Hello class, it's Ms. Augustine, and now we are ready to try some frequency and wavelength calculations. So recall that with the wave model of light, we said that c, the speed of light, or the speed of electromagnetic radiation, is equal to the wavelength, represented by Greek letter lambda, times Greek letter nu, the frequency. So speed in meters per second is equal to wavelength expressed in the unit meters times frequency, which has the unit hertz, which is the same as 1/seconds or an inverse second, as the case may be. And c, the speed of light, is a constant. That means it's always the same, and that number is 3.00 times 10 to the 8th meters per second. And recall also that the energy of photons is expressed by an equation. And again, the energy of an individual photon is directly proportional to its frequency. According to the equation, E is equal to h times nu, where E is the energy expressed in joules. H is Planck's constant, named after Max Planck. And that constant is another funny number, 6.63 times 10 to the negative 34th joules times seconds. And nu, frequency, is expressed in hertz or inverse seconds. So let's do a practice problem calculating frequency. What is the frequency of light that has a wavelength of 500 nanometers? Now remember, a nanometer is 10 to the minus 9 meters. So let's identify variables. Our equation is C equals wavelength times frequency. Our wavelength is 500 nanometers, which is the same as 500 times 10 to the minus 9 meters. But wait, that's not proper scientific notation, so let's move that decimal place over, and that's going to give us 5.00, recalling up here there was a decimal point, times 10 to the minus 7 meters. And most of the light in the visible region is going to be on the order of this 10 to the minus 7 meters, give or take a couple powers of 10. And so here, recalling that c is our constant, and again 3 times 10 to the 8th meters per second. So now we can go in and solve. So using our friend algebra, we rearrange this equation up here and solve for frequency, which is nu, and that's going to be c, the speed of light, divided by lambda, the wavelength. And then plugging in our numbers from up here, c gets plugged in here, and then we plug in our wavelength here. You'll notice that meters over meters will go away, and we will be left with the unit of 1/seconds. When we plug this into our handy-dandy calculator, we will get 6.00 times 10 to the 14th seconds to the minus 1. Now, it is noteworthy to tell you that the frequencies that correspond to visible light, so this wavelength region of roughly 10 to the minus 7th meters, will typically have a frequency in the order of 10 to the 14th inverse seconds. So let's try a second problem, and this one is from a worksheet. And again, it's asking us to determine the energy of light that has a frequency of 6 times 10 to the 14th seconds to the minus 1. And this is that frequency that we just calculated a moment ago, knowing a wavelength. So here, E is equal to Planck's constant times frequency, where our frequency that we calculated from our wavelength from the previous slide is 6 times 10 to the minus 14th inverse seconds. Planck's constant is that funny number, and the unit is joules times seconds. And E is going to be that Planck's constant times our frequency, and joules times seconds times 1 over seconds. So seconds is going to cancel out, and that leaves us with joules for our unit, and joules are the appropriate unit for energy. And we've calculated that the E here is equal to 3.98 times 10 to the minus 19th joules. Now recall here that we're calculating the energy of a photon of light. So what we just did was we took a wavelength of light, and from that wavelength we calculated its frequency using the C equals wavelength times frequency equation. And then once we've calculated its frequency using the wavelength, we can then figure out how much energy is associated with that particular photon. And since we're just talking about a particle of light, it should not be surprising that we're talking about a very small number, in this case roughly 10 to the minus 19th joules. So I like to point out that for the calculations that we're doing, our wavelengths for visible light are going to be around 10 to the minus 7th meters. Our frequencies are going to be about 10 to the 14th inverse seconds, and our energies should be about 10 to the minus 19th joules. Pretty cool. So now I'm going to take an energy practice problem off of the energy practice problem worksheet that should be in your chapter 4 packet that Mr. Palmer kindly copied for us. So problem 1 on that page says find the wavelength of light if the frequency is 4.3 times 10 to the 13th hertz. So here we're going to use our C equals wavelength times frequency. We identify our variables. C is our constant, 3 times 10 to the 8th meters per second. Our frequency, which is given in this problem, is 4.3 times 10 to the 13th seconds to the minus 1. Wavelength is what we are solving for, so we've got our question mark, and then we go ahead, rearrange our equation as we did in the previous problem. I guess 2 problems ago I lied. So wavelength is equal to C divided by nu. So speed of light divided by frequency. We plug in our numbers, 3 times 10 to the 8th meters per second for C. We plug in our frequency here, 4.3 times 10 to the 13th inverse seconds. And we solve and round to 2 sig figs, and our answer is 7 times 10 to the minus 6 meters. Again, we know we're in the visible region of light because we're close to 10 to the minus 7th meters, and we have done it. So now we are prepared. I am, maybe you're not, but we are now prepared to try some energy practice problems. Yay, problems. So now what I'd like you to do is turn to the page in your packet that's called Energy Practice Problems and give this a whirl. And at the top of the worksheet, or maybe it's the bottom, I can't remember, I give you the constants, and so you can go ahead and plug some numbers in and see how you do. I will be posting some solutions for these worksheets for you on Google Classroom, so wish I could be with you, but hope you are able to solve some problems. This is Miss Augustine signing off.